just to introduce who our speaker is. So Abigail Abeo is a robust problem solver with excellent communication and leadership skills. She's very passionate about using machine learning and medical imaging to positively enhance health diagnosis in Ghana and the world at large. Abigail is currently a graduate student at AIMS AMI, or African Masters in Machine Intelligence program in Senegal. And she also studied or was a former student at AIMS-Cameroon. And also as part of being a student at AIMS-Cameroon, she doubled as the Media Club Delegate at AIMS, where she led her team to sell beautiful experience at AIMS and also make everyone feel very important. So her research lies in image processing, machine learning, scientific computing, and mathematical modeling. Abigail is a very outgoing writer, singer, and loves exploring ways to eat and live healthily. So without much ado, help me welcome Abigail Abeo, who will be leading the session on building a regression model. So as she or when she takes over the stage, if you have any question at any point in time, feel free to leave it in the chat. Or if you want to ask the question directly would be happy to give you some time to ask your questions directly. So over to you, Abigail, and thanks so much for accepting our invitation.
Thank you, Deborah. Thank you, everyone else. All right, so my name is Abigail Abeo, as Deborah rightly said, and I'm going to mention some things before I begin. First of all, I think Deborah has sent the notebook and then the data sets to everyone. So maybe just in case you haven't seen it in your emails, you can kindly check, because we'll need that when we get into the coding part. And permit me, I don't know, I have a bit of a cough, so I may be coughing from time to time, so forgive me for that. So let me share my screen. Let me see, question screen, okay. Okay, can you see my screen? Okay, that's a nod from Deborah. All right, yes, that's fine. Okay, so good. Welcome everyone to our session on building a regression model, but particularly we're going to look at logistic regression. So this is the outline. We'll look at what regression is, and then the types. We'll also look at logistic regression on its own, and then also look at the model formulation, model training, and then an example application. So this is what hopefully we'll be going through. Now, what is regression? So regression is a statistical technique whereby you have a dependence variable and one or more independent variables, which we also call explanatory variables. And then you're looking at the relationship between these variables. Now, there are many types of regression models. We have linear regression, polynomial regression, nonlinear, ridge, lasso, elastic nets, and then logistic regression. Now, it's important to note that in these types that we have here, apart from the logistic regression, the rest are all for regression tasks. And now I know I've mentioned what a regression model is, and I've mentioned what is a regression task. So a regression task is a case whereby your output variables in your data sets are numerical or continuous. So let's say I want to predict the price of a house. I'll predict the age of someone. That's a numerical or a continuous variable. So in that case, I'm working under a regression task. Now, logistic regression is used for classification tasks. So let's say you want to predict if someone has a heart disease or not, or you want to predict if this is a color red or a color green. That's a classification problem. So that's for the logistic regression. Now, so let's go deeper into the logistic regression and then see what exactly it is. So logistic regression, first of all, it's very popular. I mean, I'm sure many of us have heard of it before and have probably used it. And it's used for binary classification. So when we say binary classification, well, binary has to do with two things. So it's either A or B. It's either a 0 or a 1. And now this logistic regression, it predicts the probability of an event occurring based on some input features from your data sets. And it's widely used in various fields, such as machine learning, in the social sciences. Okay, good. Sorry, Siri came on and was saying a whole lot of things. Okay, so yes, it's used in machine learning, social sciences, finance, and then in healthcare. So let's see what's next. So let's move on to the model formulation. Now, here we're going to go into a bit of mathematics. For those who are not, who don't have a lot of mathematical background, please don't worry. I promise not to go too technical, but it will also be nice to hear new things. And for those who have some mathematical background, this is also not going to be very, very deep, but hopefully you understand what I'm going to do. So the logistic regression, it models the relationship between the input features and then the binary outcome. Now, in this case, it's the probability of the binary outcome. So how do we get this probability of the binary outcome? We use a function that is called the sigmoid function. It's also called the logistic function. So that is where the name logistic regression is coming from. And the sigmoid function can be expressed as this function that we have here, g of z equal to 1 over 1 plus exponential of minus w transpose x. Now the w here are the weights for the model. And then the x here are your input features. So z is equal to this w transpose x. Now let's take a simple linear regression problem, y equal to, let's say ax plus by. In this case, the a and b are the weights. So in this case, are w. And then the x and y here, or let's say x1 and x2, refer to the features of our data sets. And now this sigmoid function, this is the graph of it, okay? So it's represented by this S that we are seeing here. And the output of this sigmoid function is from 0 to 1. So the probabilities that we get after we use this sigmoid function are probabilities. And remember that logistic regression is used to solve, it's used for binary classification. So either a 0 or a 1. And here lies the case, we are getting probability value. So you can get 0.2, 0.7, 0.8, what have you, as long as they're in between 0 and 1. Now we need some threshold value so that, let's say, if I have a threshold value of 0.5, and then I would say that those that fall below 0.5, I would put them as class 0. And those that are above 0.5, I'll put them as class 1. Now this threshold value can change, but usually people have used 0.5 most of the time. But depending on the kind of problem that you're trying to solve, you can change this threshold value. So how I've mentioned the weights, which are the W's that we saw, and those we also call the model parameters. Now, how do we estimate them? Well, we use something called maximum likelihood estimation. So what is maximum likelihood estimation? Well, it is a method that is used to estimate the parameters of a statistical model based on your observed data. And what you do is that you start by defining some likelihood function that describes the probability of observing the given data as a function of the model parameters. So in logistic regression, we have that the assumed statistical distribution of the data for the binary response variable is the Bernoulli distribution. I don't know if some of you have heard of Bernoulli distribution, but it is the Bernoulli distribution. And the goal of this maximum likelihood estimation is to find the values of the model parameters that maximizes the likelihood function. So in this case, we have two binary outcomes, either a 0 or a 1. So we say that the probability of being a 1 is equal to this HW of X over here. And the probability of being a 0 is 1 minus that HW of X. And where this HW of X, which we have seen from the previous slide, is a sigmoid function. And this can be written compactly as seen in equation 3.2. So let's look at equation 3.2 very well. Now, let's say that Y is 1, because Y can be either 1 or 0. If Y is 1, what do we see? The first term in this multiplication, right, goes to HW of X. And in the second term, the power there, which is 1 minus Y, and in this case, Y is 1, goes to 0. So anything raised to the power 0 is 1. So we come back to when Y is equal to 1, we get that HW of X. And now when when Y is equal to 0, we get HW of X to the power 0, which is 1, and then the rest continues. So that's this, the two statements that we have are what has been compactly combined into equation 3.2. So now moving on, we assume that our end training examples, well, they were generated independently. And so what happens here is that we have this likelihood function, which is the product of the individual probabilities that we have. And now we want to take the log likelihood. And someone would ask, well, why would you want to take the log likelihood? So it's been seen that when you take the logarithm of a function, or in this case of our likelihood function, one, it makes it easier to work with, and you're able to avoid something we call numerical underflows. So if you have a product of probabilities, small, very small probabilities, right? You get something that leads to something called the numerical underflow. So you're getting so close to 0. And so we take the log, and that also helps us to transform our products into sums. Now we take the negative log likelihood in this case. And then now what we have here is the equation down there. Sorry, that one is not numbered, but just under the using the logarithmic properties, right? So if you also remember from our high school mathematics, log of AB, right? Log of A multiplied by B is equal to the sum of what? Log of A plus log of B. So from the first equation in 3.3, we have the log of products. So that is transformed into what? The sum of the logs. So that is what we have here. And then also in this case, we want to, when you are maximizing a function, right, it's the same as minimizing the negative of the function. So that is how come we have the negative log likelihood here. So we want to take the negative. So substituting our likelihood function in here, we get this. And then finally leads us to this equation here, which is 3.4. And this is what we call the cross entropy loss, or the negative log likelihood. Are there any questions? Or I think I'll take the questions after, right, Deborah?
Yeah, I mean, unless there are questions in between that you could.
Okay, I think I would like to take the questions at the end, or maybe when we get to the coding session, then I can take questions when we're doing the hands-on session.
Okay, that equally works, no problem.
Okay, all right. So continuing, now this logistic regression model is trained using an optimization algorithm. And there are many optimization algorithms, but the one that is most popular used is called the gradient descent. And particularly, we'll be using something we call the batch gradient descent. There are 3 types of the gradient descent. We have the batch, we have the stochastic, and then the mini batch. But we will be focusing on the batch gradient descent. And don't worry, we will see what it is. So what's the idea behind this gradient descent, someone would ask. The idea behind the gradient descent is that you want to update the parameters, which are W that we have seen, right? And you want to update it iteratively in the direction that minimizes the cost function. So the cost function, which is this one that we have here. Okay, so this is a cost function. So we want to update the parameters iteratively so that it minimizes our cost function. And so how does the gradient descent work? It works this way. We first define our cost function, which we have already gotten from the previous slide. And then now we initialize some parameters. So the W, we need to initialize it. So maybe in our code, we're going to do that. We're going to set them all to zeros, okay? And then next, you want to compute the gradient of the cost function with respect to the parameters W. So you want to compute the gradient of this, and we'll also see how the final expression looks like when we get to the code. And then next, what you want to do is that you want to update the parameters with this rule as seen in 4.1, equation 4.1 here. And this alpha here is something we call the learning rate. And we're also going to see, it in the code and also see how, it works to ensure that, things go well or things go wrongly. And then finally, this model's performance can be evaluated using various metrics. And there are many of them. We have one called the precision, we have one called the recall, and then accuracy. For our scope, we're going to use accuracy. And then let's look at an example application. So one famous classification tags that you hear when people are, introducing you to classification problems is the spam email. So have you ever wondered why some emails of yours go to spam? And sometimes, well, you look at the email and then you're like, okay, I don't know what this email is. It really deserves to be in the spam. But then there are also times when you get a very important email and you find it in the spam and it's not supposed to be in the spam. Now, what happens is you can use machine learning for this. So you have examples, data, right? And you have information, which are the input features about your email. And then you have your output variable. So let's say this is an email spam. This is not a spam. This is a spam. This is not an email spam. And now you train your model on this data so that it can distinguish between the spam and the not spam. And then you can use it to now classify new and unseen emails. So the emails that go into your spam, what is happening is that the model behind the email says that, okay, based on the features, this is a spam. So that's how come it goes into your spam. So this is just an application, an example of an application where you can use logistic regression. So now we are going to delve right into the code, and I'm going to stop sharing, and then I'll move into my my Jupyter notebook, and then we'll move on from there.
Okay, so whilst you make the switch, probably we can see if there are any questions maybe. Okay, so Amma has a question that can you generate a personal algorithm to classify spam and unspam for your Gmail?
Okay, so hi Amma, what do you mean by a personal algorithm?
So from what I understood about the spam and unspam, it's more like it comes with a Gmail. But can you generate an email? Yes, can you generate an algorithm yourself? Let's say if an email has these kind of words, it should tag them as spam. you do it yourself, not the inbuilt function from Gmail?
Well, yes, those algorithms were built. So yes, it's definitely possible to do that. You definitely can. But if you want to using machine learning to do that, well, okay, so let's say that you have a spam email, okay, and then you have the input features that says that this is a spam, right? What happens in machine learning is that it's going to learn the patterns that it observes. So you may not really have an idea of the kind of patterns that is going on behind there. Or unless you want to go with a traditional kind of algorithm, not a machine learning way, whereby, okay, you would say that, okay, if you see these kind of words in there, classify it as a spam. That's also possible.
Okay.
But then the question, okay.
So that's actually my question. And if it's possible, how do you do that? Not like, I know you could do the algorithm. How do you include it into an already built system?
How do you include that into an already built system?
Yeah.
Well, that's another topic that's on model deployment.
Okay.
Which you can definitely look into. Yes.
Okay. Thank you.
Yes. You're welcome. Any other questions before we go on?
So far there are no questions yet.
Okay. All right. So, okay, let me move into my, let me share my notes to my screen. Okay. Can you see what I'm sharing?
Yes, we can see now.
Okay, you can see it, right?
Yes, we can. Yeah.
Okay, good.
Just to mention also, if you know you didn't receive the email I sent with the zip file earlier, I put a link to a drive where I uploaded the data sets as a zip file sent to me in the chat, so you can just use that to still access what she shared.
Okay, I believe I can continue now, right, Deborah?
Yes, you have to. You can. Yeah.
Okay, so this is the notebook that we're going to use. I sent the starter notebook, and I believe I hope that people will code along as I code. But well, just in case you're not able to do that, you can also follow. After the session, I'll send the notebook, the final complete notebook to Deborah, and then she will send it via email to everyone. So that's also an option. All right, so what are we going to do here? Now, we're going to build a logistic regression model to predict if a candidate will be called for an interview or not, using a data set called the HR competency score data set. Okay, and to begin, what we're going to do is first, we need to import our libraries. Okay, and the very first library here is called NumPy. And we also have, so what we are saying is that we're importing NumPy as NP. So anywhere I want to type NumPy, I will not type NumPy now, I'll type NP. It's for shortcut cases. And NumPy is a library that is used for scientific computing and numerical computations. And it allows you to work with multi-dimensional arrays, which we would see. And then pandas. Pandas is the next library, and that is, it's a library that also helps you to manipulate your data, to analyze your data and do some preparation of your data. And then Seaborn is a Python library that is used for visualizations. And it's built on top of a library called Matplotlib. And Seaborn gives very nice visualizations as compared to Matplotlib. So people like to use that. And then what we have in the next set are inbuilt methods. So we have accuracy score, and we will use it at the very end, and you will see why we'll use that. We also have train and test plates, which we'll also be using soon. And then now the logistic regression. So the idea is that I don't want to just call this logistic regression and just say, fit my data, do predictions. I don't want to do that. I want to show you how to build this logistic regression from scratch, a very simple one. And then after we have done that, I am going to now call this logistic regression here, and then we'll compare the two and see the results that we get. So that's the main idea of this coding session. So let's continue. Now, we've spoken about the libraries. Now on to the data sets. So I'm going to use pandas, and particularly a method called read_CSV to get my data. My data is a CSV file, so that's how come I'm using the read_CSV. And for those who are following along, that's coding along, what you need to do is that for this file path here, you need to get your file path and then copy that and put it here. If you, and put that there, and then when you run it, that should work. So for me, I'm using Google Colab. I've uploaded my data sets to my drive. And so I need to just mount my, let me see if it's mounted. Okay, I need to mount my drive, and then I'm copy the part of the data set, and then I'm good to go. So that's for me. So let's run this. Okay, let's run this one, the second one now. Good. So running my data set, I didn't come across any issue. That's good. Now let's look at a sample of our data. Let's really see the data. And to do that, we use the .head. I forgot to mention this. The name of my data sets, the name of the variable I gave is called HR_data. And something about variable names is that you need to give good variable names such that when you come back to your code later on, well, you can still have an idea of what the variable is doing. So if I had put something like A or B over there, the next time I come, it will be difficult to really understand what this variable represents. So since we're working with HR data, why not just name it HR data? So let's run this. And this is our data set. So, well, I can see years of experience, the columns, functional competency score, top 1 _ skills score, and a whole lot. So this is our data.
A quick one, Abigail, just a quick one. This years of experience that is in decimals, what do they exactly mean? Is it that you divide it, like, because it's like it's in decimals, so like what do they really?
Yes. Okay, sure. That's fine. So this is in decimals. So if you want to actually see, okay, I think, Deborah, I'll answer your question when I describe the data down there. Okay.
Sure. No problem. Thanks.
All right. Okay, so that's a question noted down. For the data description, let's see. I want to see the number of rows and the number of columns of my data set. And so I use this one that I've highlighted. So I'm saying HR_data.shape. So when I run that, it gives me this. So I have 300 by 10. So meaning I have the very first represents the rows, and the second value represents the columns. So I have 300 rows and 10 columns. And now if I want to see the names of the columns in detail, I can use .info, and that is what I have here. So running this, yes, I get this. So I can see the column names. I can see the number of the non-null. Non-null means the number of non-missing values. So we have 300 rows, and I can see that all throughout there are 300. So I'm suspecting that there are no missing values. And you can also see the data type of the various columns. 9 of them are floats values here. And then just one is an integer data type. Then let's just confirm that let's check if there are any missing values.
I'm
So
sorry before you move on, Abigail. I think I have another question. I'm just struggling. I'm just trying to follow up and understand
sure.
what exactly we are doing. So like with these features again, these are scores. So I want to believe that these were already pre-calculated from certain features that we don't have access to, because functional competence score, it's a score. So it's a score of certain features, right? And the same with all of the other features that you have in this data set.
exactly, yes, you're right. You're right. Because these values, let's say, how will I put it? For example, for years of experience, you don't have them, like you rightly mentioned, you don't have them in terms of the years. They have been changed into decimals, as we can see here. And I'm going to, how will I put it? I'm going to like just give, I'll take one example and give the interpretation of that. Yeah, just below. Okay. So let's check if there are any missing values. When I run this code here, let's just see what's happening. I get this, but I'm sure someone is wondering, how did I get this? So I'm going to take this .sum off here. And now we have HR_data.isNow. So you want to know if a cell is a null value or not. So if I run this, I'm getting this. This is what I get, right? So when you see false, it means that the value over there is not missing. There's actually a value there. Now, if I look at this, I can't really get to see the number of missing values in a particular column. So that is why the .sum is there, so that I can then sum up and get this. So the 0 zeros here means that there's no there are no missing values in any of the columns here. All right. So moving on, now we want to look at some summary statistics. And to get these summary statistics, we use the HR_data.describe. So when you use .describe, it will give you some summary statistics as seen here. So let's look at the years of experience. Now, the minimum here is 0 and the maximum here is 1. Now, looking at the mean here, which is 0.23, what this means is this. Now, you can change this into either months, days, or years, right? And in years, it's in decimals. So if you have, let's say, 1 year equal to 12 months, and you have 0.3 equal to some x. If you do your mathematical calculations, you cross things here and there, you'd realize that this 0.3 approximately sums up to 3 months. In weeks, that's about 12 or 13 weeks. So Deborah, to answer your question, this is for the years of experience.
Okay, all right.
And then for the functional competency score, so these are score values, right? And if you change them into percentages, 1 here corresponds to, let's say, 100%. And you can see that, well, the very minimum, okay, somebody got a 0 in there, right? And the average functional competency score is 0.57, right? So these are some statistics that you can look through as a data scientist, data analyst, just to get an understanding of your data. And to even go further, we want to look at our label column, which is the call for interview, okay? So I want to look at the counts, the frequencies of the zeros and the ones. Now, 1 represents being called for an interview. 0 stands for not being called for an interview. And we have 159 against 141. And this is almost a bit balanced, not too unbalanced, but almost a bit balanced with a difference of about 18 or so. Yeah. And then now let's look at the exploratory data analysis part. Let's look at some plots just to understand our columns a bit well. We want to look at the frequency distribution of the years of experience. And we use the seaborne, in this case, SNS, because we said import seaborne as SNS. So we use the HIST plots and you specify your data. In our case, it's HR_data. And the X is the column you want to focus on. So in this case, it's years of experience. So if I run that, I get this plot here. And what I can see is that, well, a lot of people have when you're looking at it in terms of the score from 0 to 0.1, a lot of people fall in that range with respect to the years of experience. And then again, I want to look at the top 1 scores. So the top 1 score is the score for the candidates' best skills that they have, their number 1 skills that they have. You want to look at the frequency distribution for that also. And we can see that, well, a lot of people, well, did quite well, as in scored quite well in their scores, because you can see that this data is skewed to the right. And so majority are, sorry, it's skewed to the left. And so majority are at the right side. So that's something we can see from here. And then, good, we have the behavior score. And we can see that, yeah, so majority of people also had scores between 0.2 and 0.3. That's for this one. Okay. And then we also want to look at a scatter plot, which shows the relationship between the functional competency score and the behavior competency score. So in this case, we use the scatter plot and not the HIST plot. And you specify the X and the Y, that's the columns that you want. And we have that here. So from this, well, it's we can see that it's positively correlated, not too strongly, but somehow slightly positive correlated. And so what we see is that people did well in the functional competency score. They also did quite well in the behavior competency score. Okay. Then now we want to extract the label from the data. As we have seen from here, if I go to the very last, this is the call for interview. It's part of my data set, but I want to extract it from this data set. And so I'm going to use this code to do that, which is this one. So Y equal to HR_data, and then I specify the column name, which is call for interview. So that's what I have here. And then now that I have assigned this call for interview to a new variable, I want to remove it from the original data sets because I wouldn't be needing it in there now. And so we use the dot drop to do that. And we specify axis equal to 1 in this case. This 1 here represents the column. So we want to remove it column wise. If you specify 0 and you remove it row wise, you end up with no data set. You end up with an empty data set. So you want to ensure that you specify the axis so that it knows that it's to remove it by the column. So that's for this one. And then now for the train test plates. Yeah, so here I have a question for you since it's a hands-on session. So I have a question. I'm splitting my data set into train and testing. I just want to ask, does anyone have an idea why we need to do this? Anyone?
Okay, I want to refer to your, okay, Amina, and this is what I think.
Yeah.
So with regards to the spam example you gave, you said you have to, if you want to categorize an email as a spam, you have to let the model know, like, messages with this kind of features is it's a spam, and messages with this kind of features is not a spam. So if you want to be able to do this, then you should be able to tell, if you do your testing and your training data sets, when you are training, you tell the model that, okay, if you see these kind of features, this is what I mean. Then it will give you some kind of accuracy. So when you do the testing and your results you get for the testing is close to your the training data, then probably your model is, should I say, some point or something like that. Yeah, so that's what I think.
Okay. Yeah, that's what you think. Thank you very much for sharing that. Even though unfortunately it's not correct, but I really appreciate you sharing that, because it makes me understand how to explain this part very well. So thank you, Wilhelmina. But unfortunately that's not it. Yes.
Okay.
Let me see the time. Okay, let me just move ahead since we need to get to the main part. So in machine learning, right? Why do we split our data into train and test? Okay, so let's say that I use my entire data set, okay, for training, right? And now I get a model, okay. Now I wouldn't know how well this model would do if it is deployed out there for people to use, because I have no idea. But then let's say that I have a part of the data set which I haven't touched, okay? And then let's say, so I split my data into the train and test, and then I do my training on the train part. And then now, with the model that I have obtained, I can then test it on the test part. Now for the test part, the good news is that we already have the labels for that test set, right? We have the Y, because we did a split from the original data. But I'm going to test it on just the X part and get the output from there. And then I can now compare it with the Y original from that test set. And okay, so I get to see. So let's take an example. So for this very, let's say for this very person, the actual Y test says that, okay, this person was called for an interview, right? But then my model predicts and says, this person will not be called for an interview. So I know that that's a wrong prediction there. Okay, and let's say if the actual says, okay, this person will be called for an interview, and then my model is saying this person will really be called for an interview, then I know that, okay, well, my model is doing quite well. So this is one of the idea why we do the train test and splits, the train test splits. Wilhelmina, I hope it's okay, and for everyone else.
Yes, I get it now. Yeah, thank you.
You're welcome. Good. So we use the inbuilt train test splits. You can actually write this also yourself, but I didn't want to write it. I mean, I have the code for that, but I didn't want to put that here because that's not the main focus. So I use the inbuilt one. And this inbuilt train test splits, okay, is what we called from here, from sklearn.model_selection, okay? So this is where we got our train test splits from. And then using it, I need to specify my X data. Okay, I think I didn't run this code. Okay, good. So I need to specify my X, my Y, okay? And then the test size. Now you're doing a split. What is the size that you want? You want to split it into 50-50, 80-20, 70-30, you need to specify. So I am saying here that I want my test size to be 20% of the data set. So I will use 80% of the data for training and then use 20% for my testing. Now I specify my random states as 7. This random state here, it's a value, you can change it. You can choose any other value that you want. What it does is, anytime I run this code, it's going to give me that same set of splits that it did at first using the 7. So that is just for consistency. But then I also want to shuffle the data set before it does the splits. And so that is why the shuffle is equal to true over here. So when we use this, we obtain our training, our X training, right? Our X training data to now be 240 rows by 9 columns. Remember that the original data set had what? 10 columns. You have removed 1 for the label. So you're left with 9 columns or features. And now you have split the data sets. You have 300 rows and you have taken 80% for training. So 80% of 300 will give you 240. And then the 20% of the 300 is the 60 that we have here. So this is the splits. This is the splits that we have here. So that's what's happened over here. Now I want to convert my data frames and series to NumPy because it's much easier to work with since I'm building this model from scratch. So it's much easier for me. And you would actually see why I changed them to NumPy when I do some reshaping in the code further down there. So this is the code. I use the dots to NumPy to convert my X train, my X test, my Y train, my Y test, and make them NumPy now. So I also run that. Good. Now we are ready to start building our model. Any questions up to this point before we delve into that?
Just a quick question. I'm wondering why the need of converting to NumPy again, because I was thinking from the train test splits already, you already get a NumPy array from the split. So why the need of repeating?
Okay, that's a very good question. I think, was that Deborah? Yeah. So let's just check. Let's just check to confirm the type of the X train. So I want to check the type. I use type X train. Let's see what we get. Okay, so we get no. Okay, no. Let me run this first because I've already run the bottom before getting here. So let's see. Good. So I think for whoever asked the question, I didn't get the person, but so what you see here is that this X train, after using the train test splits, is a data frame and not a NumPy. So that's why I use the dots to NumPy to change it to the NumPy. Is that okay?
Yeah.
Okay. All right. So good. Let me run this now. Okay. So let's start building the model. I'm excited. And this is where it gets a bit messier, but hopefully we'll survive. Yes, hopefully we'll survive. So a quick, let's look at some quick recaps before we delve in. Now we said we need a logistic or the sigmoid function, and we have that function here, okay? And we have the derivative here. Well, we will not use this in our code, but I just want to show you the derivative here. There are some steps that were done to get this actually. So it's not like it's something that was gotten magically out of somewhere, no. And then this is our famous cross entropy. Number 3, we have our famous cross entropy or negative log likelihood here, okay? Where you see Y true, that's for the label from the original data. And then when you see Y pred, it means what was predicted, okay? So these two, please have them in mind because I'll be mentioning Y true, Y pred, Y true, all as we move on, okay? And to get our Y pred, we use the sigmoid function. I've already mentioned that, but I'm just mentioning that again. And then now the next thing in number 4 is the derivative of the cross entropy loss with respect to our weights. And also this wasn't magically gotten. There's some steps to follow that when you differentiate number 3, you end up with number 4. And then finally, the batch gradient descent rule that we saw in the slides, this is what we have here. So this is just a recap so that we can always come back to it as we are coding. Okay. So let's move into the coding now. Good. Okay. So I have a class here called B_logistic regression. Okay. And what I put the B there to stand for built by myself, so that whenever I see the B, I know that it's built by myself, because the original, no, not the original, the built-in logistic regression also has the same name like this. So just to differentiate between the two, I put B, capital B underscore in front of it. So this is what we are building ourselves. And we're going to employ object-oriented programming here. And well, just in case you don't know what it is, well, unfortunately, time will not allow me to like really go deep into it, because that's not the focus of our meeting here. But then I'm just going to like give an idea of what a class is. So what's a class? A class is a blueprint or a template that defines the properties. In this case, we call attributes, and we'll be seeing them. And then also the behaviors, which we call methods. So these, the sigmoid that you see here, they are what we call the methods. Okay, all these, this the fit, predict, accuracy, these are the methods that we have here, and we are going to specify what they should do. And now this def init that we see here, this is a special method. So for this method, whenever we create an instance of our logistic regression class here, we need to specify these parameters that are here. And it's automatically called whenever you create an instance of this logistic regression class here. So that's for this init. Now I am going to put all the variables that I'll be needing in here. Okay, so I'm going to put them here. I have, for starters, I have this LR and this N underscore epoch. The LR refers to my learning rate here. And this learning rate is what we have here as this alpha. Okay, this alpha over here. And this learning rate, it determines the step size by which you want the parameters to be adjusted. Okay, when you are doing your gradients, when gradient descent is being performed. So you can fine tune. When I say fine tune, you can always change the values and see how it affects your model. And so this is something that will also be changing, and we'll see how it works. So I am going to start now. So I'm going to create my attributes. So I'm creating the learning rate attributes with the self.lr. And this self.lr that you see here, whenever I have the self in here, okay, it tells me that it's related to the instance of my class. And then I can always use this attributes, even though it's in this method, I can always use it in the other methods whenever I use the self. So that's why I have the self here. And yes. And then next we have the epochs. So what is the epochs? The epochs is just the iterations, the number of iterations that you want your gradient descent algorithm to go through, or the number of epochs you want to be used for the training. So let's say you can have it to be 100, 1,000, 10,000. It's also a value which we call a hyperparameter, just like the learning rate, which you can fine tune or change to see how things improve or whether they don't improve. So I'm also going to do that. And then I have epochs is equal to n underscore epochs. Then the next variable I need is something. I'm going to create an empty list that will contain all my losses. So that's something, and I'm going to name it as train losses equal to, and since it's an empty list, I use this to represent an empty list. And then finally, I'm going to get my weights, and I'm setting it to be none for starters. We are going to, how will I put it? We're going to initialize it when we get to another method. So this is for the init method. These are the attributes that we need to begin with. Then now let's code up the sigmoid function. So this is what we want to code. This sigmoid function over here. The 1/1 plus exponential of minus z. So that's what we want to code. Okay. And how do we do that? So let's say that I'm going to name it as zig func. So whenever I see this, I know that, okay, this is sigmoid function. Okay. And the numerator was a 1. So I do 1 divided by. Then I start, this is to code the denominator now. So I'd say, sorry. So I'd say 1 plus, right? And now for the exponential, I'm going to use NumPy's exponential. So I'd say NP dot, because NP is for NumPy, right? And as soon as I do dots, you can see the different methods that we have, right? So I'm going to use the EXP, which is for the exponential. And we have minus here. So there's a minus here, right? And then the Z, I'm going to specify my Z. But then remember that our Z is this. Our Z is our XW. Okay, so this is a matrix multiplication, a matrix product. So Z is XW. So I'm going to represent that here. And then I would say X. Then I'm going to use this symbol here. Good. And then self.w. Okay, so this is the sigmoid function which I have written here. And then I'm going to return it. So return zig underscore func. Okay, so this is the sigmoid function that we have written here. Is everyone following, or do I need to go over something? Okay, since it's quiet, I think I can continue.
Yeah, you can.
Then now, so we've written up our sigmoid function. The next thing we want to write is this cost entropy here, right? This one here, this one is long. We'll take it a step at a time, right? Let's see. So first off, this is what I'm going to do. Let's write this one first, okay? Let's write this one first. Then the next thing I'll do is to come and write this one, okay? So let's start off with this. And this is our y true times our log spread. Good. So let's see. Okay. So our y true, we have it here. And then times our y spread. Now we need our y spread, but there's something missing. Okay, let me write y spread and you see something. What do you see? You see that it has highlighted y spread because it doesn't know what y spread is. It's seeing y spread as a very new thing, right? And remember that y spread is gotten by using the sigmoid function, okay? So since we already have written the sigmoid function, I will not rewrite it again. I'll just call that method in this cross entropy here. So I would say y spread is equal to, now if you're using a method in another method, you need to also use the self. Okay, so I have self.sigmoid. Okay, and then x. So now you can see that this y spread is no longer underlined because it knows what it is. Okay, so that's for this first part successfully written. Now let's go to the second part. The second part is this. Y minus y true times log of y 1 minus y pred. Okay, so let's also write that here. There's a plus here. Okay, so let's see. 1 minus y true. Okay, so y minus y true. And then times, yeah, the log. So log, I'm also going to use NumPy's logarithmic method here. So np dot log, that's how we write it. And then it's, we are taking that for 1 minus y pred, right? So I do 1 minus y pred. Good. Now we are not done. Okay. So we need to, you can see a summation here, and you can see 1 over n. The n there stands for the number of rows, okay, of the data set. So how do we get that? Now you are summing and dividing by the number of rows. Okay, so instead of using a sum and then doing a division again, I can just use a mean. So I can just use a mean straight away. And now this I would do, so I would do np dot mean. Okay, and then I need to put everything now in brackets. We have to be careful about our brackets, because if not things will get messier. So let's see. Wait, let me close. So I want to close this one because they are together. Okay, let me show you. So you remember that we put the y minus 2 times the np dot log. I'm closing them all together now, right? That's why I have an extra bracket here. Good. And then now I can, so this is my loss. I can say loss is equal to this. But now there's something else. We need to specify the axis. Okay, the axis. And we want to find the average column-wise. Okay, and we're going to use axis equal to 0. I know that, I think, well, which one did I use? I used axis somewhere here. Good, I used axis over here, and then I specified it equal to 1. So it turns out that pandas and NumPy like have different ways of representing the axis. For NumPy, right, when you want to specify column-wise, you use 0. Okay, that's for NumPy. But if it was pandas, would have used 1. So it's always good to check the documentations of the methods that you are using so that you get familiarized. It's not something that you have to, well, as in keep in mind, but as over time, you get used to knowing which one it is. But it's normal if it confuses you, which one is, because it also confuses me at times too. So now that we have our cost entropy written, I am going to say return loss. Okay, so I have that here. Then now let's get to the fitting part. This is where, okay, is that a question?
Yeah, sorry, are we missing a log at the y true times y predict in the formula?
Okay, let me just check that.
Times log.
Good, thank you very much. Yes, this log, right?
Yes, that log, yes.
Exactly, thank you. It means you're following, thank you. So let's put that there. I'm sure we'd have finished running this thing and maybe would have had some errors. Okay, so let's see. Good, I need to close this now. Good, so let me just check. This bracket is for, yeah, that bracket, and this bracket is for this bracket. Good, I think now everything is okay for the cross entropy. Thank you very much. Yeah. So let's get to the fitting part now. So the fitting part, this is where we're going to use the gradient descent algorithm. And I did mention at first that we first need to get our cost function, right? And for our cost function, let me see. Yes, so we already have, which is this one over here. Okay, so that's what we have here. And then we also need to initialize our weights. So let's initialize our weights first. So I'm going to initialize our weights. Let me just put some comments here so that my code initialize the weights. And now we're going to initialize them by zeros. Okay, so I'm going to say self.w, self.w, let me see. Good. Self.w equal to mp.zeros. So that will initialize them as zeros, but we are not done. We need to specify how many rows we want. Okay. Now the weights, the number of weights correspond to the number of features in your data set. So in our data sets, we have 9 features. Remember, 1 was for the label, so we were left with 9. So I need to specify 9 here. I can put 9 by 1 here. So that's like 9 rows and then 1 column. But this is not a good idea because I want this to work for all kinds of data sets. And so it's rather best to put x.shape here. But then since I want the column, I specify it with a 1. So what this does is, if you say x.shape, it will give you, good, I think I have something over here. What was that? Yeah, when we said hr_data.shape, we got 300 by 10. So 300 was for the rows, 10 was for what? The columns. So if I want the columns, I specify a 1, and that would give me the number of features. So that's here. So we have initialized our weights. Good. So now we are ready to do the iterations, that is looping through our iterations. And what we need to do is we need to use a for loop. Okay. So we're going to look through the number of epochs that has been provided, this self.epochs. So instead of saying for I in range of self.epochs, okay, sorry, with a colon, I would want to say for epoch in range of self.epoch, so that's okay, I get to see that I'm working with epochs. Okay, so epochs, 1 epoch is just 1 epoch, right? And then here we want to get the gradient of our cost function. We want to put our gradient here. So let's look at our gradient. This is the gradient of our cost function here, right? Now you can see ypred. I'm sure you cannot see ypred here. And we've seen so far that whenever we mention ypred, we need to go to what? The sigmoid function. So to get my ypred here, I'm going to do ypred is equal to self.sigmoid of my x, which is this x, okay? So that's what I have here. So let me put a comment here that says, this is making predictions. Good. So now we can code up our derivative of the cross entropy, which is this one. So I have x transpose by y true minus ypred. So let's write that one first. Let's just write this part first, okay? So I have, okay, so computing the gradients. This is just for comment's sake. Good. So now we have, it was x transpose, and you can represent it as x dot t. That's for transpose. And then we have, and it was, what was it? Y true minus ypred. Yeah. So y true. Okay, in this case, it's y, right? Please see this fit here. This fit has x and y, not y true. So I need to make it a y. So that's the y over here. then minus my y pred. Okay, so that's what we have here. Good, that's done. Then now let me put this entire thing in a bracket. Okay. Good. And then now I need to specify this one, this minus 1 over n. Okay. So this n here is the number of rows again. Okay, so let's do that. So I have minus then 1 divided by, and again, I'm going to use the shape. And since it's rows, I specify 0. And then, good, we have a times for that. So this is our gradient, which I'll call DL. So I'm assigning a variable called DL to it. Okay, any questions up to this point?
Just a clarification again. I think we are using y here. Is this not y true from the
Sorry. Which part?
The computation of the gradient. So we say y minus y pred. So I guess this y is y true. So, right?
Yes. Okay. Yes.
Okay.
This
So you
y,
said it as, okay. You said it as y in this method. Okay. Yeah. Still
yes.
work.
The fit here is x and y.
Yeah,
So the y is for the true, but since it's not named as y true here, we need to put what is in defined in the that parameter. So that's why we have a y here. If it was y true, we would have put y true over here.
Yeah. I forgot to check the method. Yeah.
That's fine. Okay. So good. We have this now. Now, let's see. We need to now do the updates. Okay, we need to do the updates now. So updates, we say we have, so we have W equal to W minus alpha of the gradient times the gradient, right? So let's see how we write that. So let me see, let me put updates rule here. Self.w is equal to self.w. I will explain something here before, and then we have self.learning rates, then times, let me see again, good. Yes, then we have DL. So why do I have self.w here and then self.w here? So what this self.w here before the equal is the new one, and then this one is the old one. So it's like you're updating the same variable as you go through the iterations. So that's what's happening here. And then we have our learning rates, and then we multiply it by the gradient of the loss function. So that's what we have here. And we are almost done. Now we want to get the loss. Remember that we want to see how the loss is reducing as we go through the epochs. So we created a self.train_losses here. But before we can, let's say, put these losses in there, in this empty list, we need to actually get the loss. So let's get the loss. And we have already created a method called cross entropy. Okay, so that's what we have here, cross entropy. So I'm going to say loss is equal to, then since we are bringing a method inside another method, we need a self.cross entropy. Now, this cross entropy takes your x and your y true, and that is what we also have here as x and y. So I'm just going to put x and y here. Okay, so that's what we have here. Then now I can append my losses. Self.train append loss. Okay, this is 3s. Okay, so this is what we have. Okay. Then now let's do something also here. I want to print my losses. Okay, I want to see as it's going through the iterations, I want to print them and see what is happening in there. Okay, so I can say loss for epoch. Then I want to specify the particular epoch. So this will take, so this epoch here, right, is corresponding to this epoch here. Okay. So then I say loss. So this loss here is corresponding to this loss here. Right. Now, just imagine that you have 1,000 epochs and you've put a print here and you want to print, and it's going to print 1,000, it's going to print 1,000 lines. That's a lot of lines, and I don't want that. So what I'm going to do here is I'm going to put an if condition here. Okay. And this if condition here, what I'm going to say is if epoch, so okay, let me explain what I'm going to do before I write it. So if I have 1,000 epochs, right, I want to only show the epoch, the loss at epoch 0, epoch 100, epoch 200, epoch 300, up to 900. So in that case, I only have 10 different statements, which is much better than having 1,000. So I say that if you are at a particular epoch value, and when you divide it by 100, your remainder is 0, then print this. So now I put this in indentation. So yes. So now if my epoch, so if let's say I have 100 divided by 100 gives me a remainder of 0, so it will print. But if I'm at 99 divided by 100, right? You know, the remainder is not 0, so it will not print at that point. Good. So that's for the fitting part, and we are done with the fitting part. Now let's quickly move to the predicting part, because so this fitting is for training. Now after training, we need to do the predictions, right, and see what is happening. So how do we do the predictions? To do the predictions, again, we need a sigmoid. Okay, so we need to call the sigmoid. And to call the sigmoid, this time I'm going to use this variable name called proba. Okay, so let's see, solve the sigmoid of x. Okay, why did I name it proba? So we know the sigmoid outputs probabilities. So proba is just some short form for me for probability. So that's why I have proba over here. Then let's do something interesting. We did say that it's going to output probabilities, but we only have 2 classes, 0 or a 1. So now we need to set a threshold such that if you are below, let's say that threshold, you are a 1. If you are greater than that threshold, so if you are less than the threshold, you are 0. If you are greater than the threshold, you are a 1. So how do we do that? I can use a for loop, but I would want to use something we call list comprehension, and let's see how that works. So I would say you are 0 if P is less than or equal to 0.5, else you are 1. Oh, my else is wrong. Else you are 1. Okay. And for P in proba. Okay, then I'll call this my output. And I need to return it. Good. So we have written the method to make our predictions now. Any questions over here? Okay, good. Then lastly, our very last method is our accuracy. So how do we get the accuracy? Okay, so now let's analyze something here. If my actual, let's take an example, okay? If the actual Y was that you were called for an interview, And then I also predict truly that you were called for an interview. That's a correct match over there, right? That's a good, so we count that as a 1. But then if there's a mismatch, that's a wrong prediction then, so we don't count that. So let's say that I have five instances and I get 3 of them correct and the remaining 2 are wrong. If I want to look at how accurate that then is, right? I would count the number of correct in there. So 3 correct, that's 3, and divided by 5. And then I have what? 3/5. So that's the idea we're going to use over here. You have your Y true and you have your Y pred. You want to get the counts of when they match. But this time you also want the mean of that so that you get it in terms of fractions. So let's see how we write that. I'm going to say when Y true is equal to Y pred, okay, you want to get the mean of that. Now, so in the example that I gave of the 5 cases where 3 are correct and 2 are wrong, that's 3/5 and that's 0.6. That's in terms of fractions. But if I want it in terms of percentages, I just multiply 100 by it and I get 60%. So my accuracy is 60%. And so I want to put 100 here times 100 here. And then I name this as accuracy. Then I say return accuracy. Good. So now we are good to test our inbuilt logistic regression model now because we have everything that we need. So let me quickly test that here. Let me put a comment here that says testing our model. Good. So to test, okay, I need to run this. This has not been run. Good. So I'm going to create an instance of this class called model_B. And please, if you remember, whenever I see B, it just helps me to know that, okay, this is something, it's related to the class that we built ourselves, okay? So I'm going to create an instance of the logistic regression class that we just built. And I did mention that what the parameters you have in your init method, they must be, you must have them whenever you are instantiating, you're creating an instance of the class. So we have the learning rate and the number of epochs here. So I'm also going to put that here. So I'm going to say learning rate, well, let's start with 0.01 for beginners. And then the number of epochs, let's say 1,000. Okay. So let's run this and see. Good. So this is run. And now let's do some training on our training data. So to do the training, if you remember, we need the fit method to do that. So I'm going to say model_B, because that's the instance of our model, .fit. And I'm going to put X train and Y train, because those are these two correspond to this X and Y here. Okay, so we run that. Let's see. Okay, so there's an error. It says that B logistic regression object has no attribute epochs. So let's go to where this error is coming from. Voila. So the issue is that, please look at this. My attribute is called self.n_epochs, but I made a mistake here and put just epochs here. So let's correct that and run this and run this and run this. Okay. So let's see. Okay, so let me see something in here. If epoch, Okay, so let's see, let's go to NP for this. And then I have my prints here. Okay, this is not the kind of output I'm expecting. Okay, so let me do the predict and see something. So let's say y pred is equal to model underscore b dot predicts, and then we have x test. Okay, so we have an issue here. It says that output is equal to the truth value of an array with more than one element is ambiguous. Use a dot any, and let me see something here. Okay, so it has an issue with this one here. So let me go quickly to that and see what is happening here. Okay, let me comment this one out. And this one. Okay, so it says 0. Let me see something. 0 if p is less than or equal to 0.5, else 1. Yeah, that should be correct. Okay, let me see something. Okay, so if I do things proper and I run this. Okay. It's ambiguous. Use a dot any or a dot all. Interesting. Please give me a second to just quickly see what's happening here. Okay. Okay, that's a 60 by 9. And this is type. Okay, so it's NumPy.
I think maybe we should use parentheses in the condition, like the probability. Yeah, like it's 0 if this condition, so like just the probability is less than or equal to 0.5 in parentheses.
Okay, let me just write that and see. You mean the 0.5 in parentheses?
Yeah, so the whole the whole condition there, like probability of it's less than or equal to 0.5.
Okay.
That is parentheses.
Okay, it's still giving us an error. Let's see. It's supposed to work. This is strange. The truth value of an array with more than one element is ambiguous. Use the a dot any or a dot all. So I have a prober here, and I'm saying that it's 0 if let me remove this, or is it 1? Copy and prober. And wait, good. I printed my probers. Yes, so these are the values. Oh, okay, let me see something. In my whiteboard, okay. Okay, let me print the shape of this and see something. Okay, so that's a 60 by 240. No, good. So I'm not supposed to get a 60 by 240 because we are getting predictions. So I'm just supposed to get a 60 by 1. So let's see what's happening. So this is 60 by 240, and that's not supposed to be. Good. I forgot something. Okay, so let me just do something here. Now I need to do a reshape here. So y dot reshape. Hopefully this should work. So please let me run this first, and then hopefully it works, and then I explain why I had to put that there. Good. Okay, perfect. This is it. So please look at something over here. We got 60 by 240. And what happened was that here, where is that? Here, okay. My y pred is a column vector. Oh, let me see. Yeah, it has 60 items in there. So it's a column vector, but then the y is a row vector. Okay, so you have it this way. So we need to make sure that it also the y becomes what's the name? A column vector. And so that is why I did a reshape here. Now, why did I put -1 and 1 here? Since we want the number of columns to be 1, we put 1 here for this second number here. And when you put a -1 in the other parts, Python figures out what the number there should be. So let's say that you have a row vector with 10 elements, and you want to change the shape and make it, let's say, 2 by 5. Okay, if you put 5 here, Python will automatically recalculate it and know that, okay, this should be a 2 over here. So that's what we have here. So let me just, okay, so let's check the accuracy and see. So I'm going to say accuracy underscore B is equal to model underscore B dot accuracy. Okay. And what we have, so we need the y true, and y true is our y test, okay, in this case. And then our y pred is this y pred that we have here. So I'd say y pred, and let's get the accuracy. Okay, it says good, 5B. Good, so we have a model. So we built a model, and when we test it on our accuracy, so when we test it on our test sets, we have 46%, which is not good. So let's fine tune the learning rates, for example. Let's try the learning rates. So instead of 0.01, I'm going to put 0.1 here, and let's run that and see. Good. So, whoa, we have 83.3. So do you see how, changing the learning rate from 0.01 to 0.1 has improved our accuracy? So these are, you can also change the number of epochs to see if it goes further on. But because of time, I'm going to just quickly use the inbuilt function now. Okay, so so that we can compare and see what happens. So using inbuilt function now. Okay, so what do we have? So we have logistic regression. Okay, so we said from sklearn.linear underscore model, we import logistic regression. So I'm going to use that here. I'm going to create an instance and say model is equal to logistic regression. So this doesn't have the B, so we get to see that this is the inbuilt one. But there is another thing we need to specify here. If you noticed, or let me just say this, we didn't use any bias in the inbuilt one that we're doing. And so just to have the two cases on the equal side, I am also going to put off the bias over here. Okay, so I'm going to say fit intercept is equal to false, because by default it is true. So we're going to say it is, put it to false here. So running this, now let's do a model.fit. And we need our X string. So this is just the inbuilt one. And you can see how simple it is. You are just calling things and then you are just running them. And then now let's do a ypred. Okay, so let's say this is, let me just say YP, okay? because I use a YPRED in the above. So I'll say YPRED is equal to model dot predict, okay? And then you also specify X test. And then we have this. Now let's get the accuracy. So I also say, which name should I give it? Accuracy. Okay, I use accuracy in the, okay, we use accuracy underscore B here. So let's use just accuracy here. So accuracy is equal to, and this is where the accuracy score comes in. This accuracy score that we brought in, okay? The inbuilt one. So we're going to use that. And we would say it's what? So that's accuracy score. And then we need a Y test and the YPRED, which is Y underscore P. And let's call accuracy. Wow. So please look at something. Using our logistic regression that we built ourselves, after improving the learning rates, we get an accuracy of 83.334 here. And when we use the inbuilt logistic regression, right, and making sure that the bias is set to false, because in our own, we also de-include the bias, we also get the same accuracy here. So this brings us to the end of our hands-on coding session on the logistic regression. Just to give a quick recap of what we have done, we have looked at what regression is. We have looked at the types. We have seen that there are ones that you can use for regression tasks, and there are ones that you can use for classification tasks. And we have also seen how the logistic regression model is formulated, the training, and we have also seen an example. And now we have used a data set on HR competency to predict if someone will be called for interview or not. So what we did was that we built our own logistic regression class, and we got an accuracy of 83%. And when we also called the inbuilt logistic regression, we also got an accuracy of 83%. Thank you. Any questions?
Thank you so much, Abigail. I don't know if there are any questions.
Go, Abby.
Is there?
Are there any questions? And I think, yeah, like I said, Deborah, I would send the final notebook with like comments nicely written out so that you can forward it to the learners.
That would be awesome. Yes. So I hope to get that and I'll share with them. So if there are no questions, I think this probably would be a good place to wrap up. And I should say from the co-organizers of WiMLDS Accra Ghana chapter, I want to say a very big thank you to Abigail for taking the time to prepare this lecture. It was very interesting and very, very refreshing for me in particular, because the last time we did this coding from scratch was like around 2019 in Army. So it was really good to get a refresher on it. So thank you so much. And I hope that each and everyone also learned something new from this. So we hold these meetups again every month, and hopefully next month we'll be having another session. And so look out from our social media, Twitter or any other place for updates as far once we fix the date, and then the facilitator for it also would share the materials once Abigail sends them to us. So yeah, so much, Abigail. And
yeah, and I think I've seen Emmanuel's message. Yes, I will include the slides as well.